next speaker is Julia Medvedeva, who's a professor at Missouri University of Science and Technology. Julia obtained her PhD from the Institute of Metal Physics at the Russian Academy of Sciences in Ekaterinburg in 2002. Afterwards, she was a postdoc at Northwestern University before she took up her position as professor at Missouri. So Julia, we're looking very much forward to your talk.
Thank you so much. Thank you so much, Johannes, for the introduction and for inviting. I'm really honored to be part of this group. And I wish I would be in person in London. We all probably would say the same. I hope that soon we will be able to travel. I actually never visited UK, so hopefully sometime soon we will be able to do it. So let me start my presentation. Let me know if you can see it, and I hope everything is good. Yep. So thank you. Yes. So my talk is about amorphous oxide semiconductors. And first question, of course, is what those materials are. So here are some really fascinating, a few fascinating results about these oxide semiconductors. So unlike silicon semiconductors, amorphous oxides of post-transition metals, and here I'm talking about indium, tin, gallium, zinc oxide, exhibit optical, electrical, thermal, mechanical properties that are comparable or even superior to this to those possessed by crystalline counterparts. So this is the first unusual quality of these materials that, again, unlike silicon, we know that the properties deteriorate significantly when we go to amorphous phase. Here, it doesn't happen. In fact, carrier mobility is on par to the crystalline phase, 10 to 60 centimeters squared to volt per second, and it's much, much greater than amorphous silicon even after hydrogenation. They, of course, require low temperature deposition. It's low cost. We can deposit these materials in large area, uniform, flexible films with smooth surfaces. We can tune band gaps, optical band gaps. These materials are transparent in the visible. We can tune work functions with the composition, and the number of carriers can be tuned over very wide ranges from semiconducting to very high carrier mobilities. And of course, the biggest market right now is in flat panel displays, although these materials find a lot of applications in many optoelectronic devices and beyond. So there are some challenges, and here I start from the very first one, kind of to put a difference between, again, the silicon semiconductors or germanium-based semiconductors and also glasses. In all these materials, we have covalent bonding. We know exactly the distances, and this is a strong bonding in both, again, silica and silicon. But unlike those materials in oxides of post-transition metals, we are dealing with ionic, much, much weaker metal-oxygen bonding. And this can be seen right here, that the second peak, oxygen peak, is suppressed, which tells us right away that we have very strong distortions in the metal oxygen polyhedra. So the first peak survives when we go to amorphous phase, but after that all the features are suppressed, including even the second peak that is a feature of the glasses, for example. So because of this weaker metal oxygen bonding and strong distortions, but also because we are interested in the transport properties of this material, so defects are very important, optical properties again are very important. We have to use ab initio molecular dynamics and density functional or hybrid functional, actually go beyond the DFT a little bit to describe these local distortions, defect formation, carrier transport, carrier generation, and optical properties in these materials. Challenge number 2 is the actual origin of carrier generation in the amorphous oxide semiconductors. So I'm a theorist, but I will be talking a lot about experimental results of my collaborators. So here, these are experimental measurements, just hole concentration from the hole measurements in indium oxide. And in the middle, you can see that this carrier concentration depends on the temperature of deposition. So essentially at high temperatures, when we deposit by pulse laser deposition, we have a crystalline films. Then there is a area that I will talk a little bit more later. As we decrease the temperature, we start to develop amorphous phase, and the materials become truly amorphous at 0 degrees, X-ray amorphous. So as you can see, the disorder increases the carrier concentration. And again, it's a very marked contrast to the typical semiconductors. When we go to disordered structure, typically the carriers reduce, but here we have 2 orders of magnitude higher carrier concentration in indium oxide. More interestingly, even when we tune the oxygen pressure by fixing the deposition temperature at -25 degrees, so we are truly in the amorphous phase, and now tuning the oxygen pressure, the change in the carrier concentration is much more moderate. Still, of course, we can tune it a little bit, but interestingly, in other systems, for example, zinc tin oxide, the largest carrier concentration has been found for the materials that are over stoichiometric. So we have more oxygen that is stoichiometrically expected, and still these materials have high carrier concentration, electron concentration in the materials. So something is really unusual happening, and this is the first clue that the defects that we are used to, oxygen vacancies in the crystalline materials, they're very fundamentally different to the amorphous oxides. We cannot actually even call it a vacancy, right? Because we don't have sites in amorphous materials. But as in my talk, I'll try to describe that the defects really differ fundamentally from the crystalline oxide. So we need to develop these metrics and descriptors of how we can deal with the defects, how we can describe them structurally and electronically as well. Finally, again, unlike many materials, well, definitely the crystalline materials, when we dope the material, in amorphous oxide, we don't see a change in the carrier concentration, very little change. So these additional ions like tin 4+, gallium 3+, zinc 2+, if you put it in the indium oxide, which is 3+, they do not serve as carrier donors, so they don't dope the system. Of course, they affect the properties significantly, and again, I will be talking about it, but they are not dopants in the sense as we used to them in the crystalline materials. Finally, challenge number 3. And these are complex deposition structure properties. So these materials have been studied for quite a while, and still there is a huge gap in understanding and predicting the properties. And we know both from experiment and theory that the structure and properties of these materials are extremely sensitive to deposition conditions, post and pre during the deposition conditions, oxygen stoichiometry, metal composition. And that makes the available research data quite scattered and often hard to reproduce. So the parameter space is so large for these materials, and again, the growth conditions are so diverse that we really need to develop some microscopic understanding in order to have some predictions, because just impossible to do empirically sample by sample approach. So our goal is to look at different parameters that may control the properties and separate them, and then develop a theoretical model of these materials. Here is the 4-dimensional parameter space for amorphous oxide semiconductors that I will be looking at this talk. So first we will talk about deposition temperature and how that affects crystallization and transport regimes, how we can go from bulk conductivity to multi-phase percolation to hopping and localization. This is probably one of the major parameters, but of course that's not the only parameter that controls the properties. Metal composition affects the nanostructure, mobility, band gap, work function. So again, that is what is expected. And so we need to separately look at the metal composition as well as the deposition temperature. Oxygen stoichiometry, obviously, I already mentioned that seemingly controls the carrier generation and scattering, but it's not, again, that simple. So we have to look at separately at the oxygen stoichiometry, but then combine it with the previous parameters as well. And finally, I will briefly address the geometrical constraint. This is the work that we recently started on surfaces and interfaces and how geometries affect the structural and electronic properties in these fascinating materials. So let me start from the deposition temperature. And these are, again, measurements by my colleagues from Northwestern. So what we know for the indium oxide specifically is that as we lower the deposition temperature from 600 to all the way down to very low temperatures for the deposition, we can go from the crystalline material to some phase percolation and then X-ray amorphous. So if you look at the X-ray, that the peaks are gone, and we can calculate the crystalline fraction from there, which is also shown here in green. And the peaks are gone. So in terms of the X-ray, we can call this material amorphous after 0 degrees Celsius. However, if you look at the nanostructure, and these are cartoons, of course, but what have been observed from the TEM resolutions, for example, high resolution approaches, is that we still have some nanocrystallites inside this material. Those nanocrystallites, however, just decrease linearly, so they are unable to explain the mobility peak. So the black curve that I'm showing here is the electron mobility, and as you can see, the mobility goes down as we go from the band conductivity, just simple scattering on the grain boundaries, ionized scattering. It reduces, of course, because we start to develop an amorphous phase that grows, so we have phase percolation, and then the mobility increases back up just at the onset of the transition to truly X-ray amorphous material, and then drops back, which can be explained by strong localization. But of course, the question is what happens here, how we can explain this peak, because again, just the nanostructure, the size or the density of those nanocrystallites alone, they cannot explain the mobility peak. So first we have to start from the structure, looking at the local structure of indium oxide below crystalline to amorphous transition. First, just the general radial distribution function. And here I compare the experiments just around the peak, so 25 degrees slightly above, and then 2 data points that are below the mobility peak, as well as theory. So what we can see is that the first shell peak is showing very weak dependence on the deposition temperature. So the position of the peak does not vary that much. There is some broadening, of course, but generally the first peak survives. However, there is a significant change. There are significant changes for the second and third shells, which corresponds to the sharing between the corner and age-shared polyhedra. So indium, indium, metal, metal, distribution is affected. Now, how we can align the theoretical cooling rates, we are using molecular dynamics and different cooling rates with the deposition temperature. Well, we use the experimental exhaust measurements and then got the information from our theoretical modeling on the distances in the first and second shells, third shells, and also the coordination. And we compared the scale in the deposition, experimental deposition temperature to the theoretical scale in cooling rates for different cooling rates. And we got quite a good agreement. Again, for the structural here, I'm showing only the coordinations, but we also done the distances and the distortion factor. So we are comparing really good, and that gives us hope that now we can understand that mobility peak based on the just different cooling rates in indium oxide. So what's fascinating here is that the second shell coordination is suppressed from nearly 6 to 2 in indium oxide, and indeed the age sharing is broken. So from 50% age shared, 50 corner shared, when we go to amorphous phase, we switch to almost 70 corner shared and 30% age shared pairs. Well, the first peak is not changing. So indium oxygen distances are similar, at least on average. And that's why the electronic properties are actually very, very good in these materials. So despite that we have an amorphous phase, because again, the nearest neighbor indium oxygen distances are very similar to the crystalline, the overlap is not very much affected because indium is an s orbital. And again, this is an ionic material, so we have the overlap between the oxygen p orbitals and indium s orbitals is not really affected. And that's why at the bottom of the conduction band, we have a very delocalized states. So at least in the stoichiometric and weakly under stoichiometric material, still we have very delocalized states. So the only localization occurs at the valence band, at the top of the valence band as we go from the crystalline to amorphous material. But again, the conduction band is very delocalized. And here we can plot even the bottom of the conduction band. We still have the parabolic conduction band similar to the crystalline materials. Effective mass is actually slightly even smaller in amorphous case. And that is, again, the first clue, the first explanation why the mobility remains so good as we go to amorphous phase. Here on the side, sorry, I keep switching because of my mouse. So here on the side, the conduction band states are shown. So this is the charge density only in the conduction band. And what you can see is that let me choose actually a pointer. So what you can see is that not all atoms contribute to the bottom of the conduction band. So it's not quite uniform. Some atoms contribute more than the others. And we actually developed some understanding what contributions, electronic contribution, how they can be predicted based on the structure while looking at the coordination, distances, expected distances, distortion. We actually found the dependence, which atoms contribute more. But if we focus on actually atoms that do not contribute or contribute very low, these are typically the fully coordinated indium atoms, 6 coordinated, similar to the crystalline material. Then we can look at the distribution of those atoms. And what we found is that those atoms form so-called chains just near the onset of the mobility. So here again, I'm plotting the experimental mobility. This is the same peak as I just showed, but zoomed into the closer range of the temperatures near the transition itself. And at the same time now I'm plotting the cooling rates. and we are confident that we can put these scales together, the experimental deposition temperature scale and the theoretical molecular dynamics cooling rate, because we did that scales based on the structural comparison between experiment and theory. And so what we find here is that when we cool the structures very fast first, then of course we have a random distribution of those fully coordinated indium-6 atoms as expected for the truly amorphous phase. When we cool them very slow, and here the slow is about 5 Kelvin per picosecond, then we start seeing clustering of those 6 coordinated, which is actually the initial step for nucleation of those nanocrystallites that we see on the experiment. But intermediate cooling rates, about 200 Kelvin per picosecond, we see that we have the chain formation, so long chains of these fully coordinated materials actually help to develop the conductivity chains in these materials, and we believe this indeed explains the mobility peak in this material. We can take that step further and actually predict what will happen to different materials. So here I'm showing again experimental results for indium oxide. Again, that same mobility peak, just on the onset of the crystallization, we have the peak, and the same happens in zinc indium tin oxide. The peak is shifted, and the mobility doesn't go as low below this peak. So again, the red point in Zito, zinc indium tin oxide, corresponds to the transition to X-ray amorphous. And again, we have a peak just at the onset, but again, based just the structural motifs and the morphology in zinc indium tin oxide, we can tell that indeed the transition temperature should be shifted as expected. Of course, we have more components in this system, so we need there will be higher temperature rate for the crystallization, which is good and practical from application perspective. But again, based on just this, looking at the structure, we can see that the presence of zinc and tin prevents clustering that we've seen in indium oxide and nucleation, and that's why we have a shift in the temperature and shift in amorphization as well. And also we have higher mobility in Zito below this peak, and this is again agrees with what we are seeing from the structure of Zito. Zinc and tin increase the number of indium-06, and then they enable this chain formation that we need at the same time. So that's why the mobility doesn't go as low. So just very simple considerations of the morphology. Once we know the atoms that are responsible for the conductivity path, can give us predictions on the mobility. And we also have done it for some other materials, such as indium zinc oxide, indium tin oxide, or indium gallium oxide. So again, here, these are the experimental results of the carrier mobility as a function of the doping, so the fraction of the X element, tin, gallium, or zinc. And just looking at the structure, we can tell that zinc favors chains, and then that's why it has the best mobility overall. Tin actually helps a little bit, but only up to the point, up to 10%, because after that tin tends to cluster itself, and so that's why we have a limited mobility. As tin fraction substitution increases above 10%, it drops significantly down, and then gallium disconnects the indium-6 and cluster itself. So we have a very strong scattering and low mobility, and mobility goes down quite significantly among these three. So here we can put place also Zito, and actually we can predict the the mobility, what we would expect just based from this morphology in different compositions. Just to take a little bit a step further, for the indium gallium oxide, actually we've done a collaborative work, again experimental and theoretical, by looking at even higher gallium content. So before I showed you up to 20 or 30, but now it's up to 40%. And in agreement with the previous slide, the mobility drops down significantly, as well as the carrier concentration, but it saturates, and it's not falling further as we keep increasing the gallium content. So that was very puzzling when the observation was made, why we are not reducing the number of carriers, and the mobility is not reduced as we go beyond some point in gallium content. And using the simulations of indium gallium structures with different gallium content, what we found that again, morphology is likely the cause of this mobility being stable and not going further. So there are competing phenomena that occurs. So first we have the indium oxide and chains, very good, just no gallium. As soon as we start putting gallium, we are breaking some of the chains. So gallium does disrupt the chains initially, breaking, depleting the conductivity channels. But above 20%, what we see is that the structures favor the chains of gallium itself. And although gallium does not really contribute to the conductivity, it promotes the conductivity through the remaining indium states. It's a weaker conductivity, of course, a bit weaker mobility, lower carrier concentration, but still just simple morphology really helps explain the observation of the properties in these materials. And so it should be considered as well as the local structure, the longer range, medium range structure needs to be considered as well. Finally, these are very recent results, but very fascinating. And this is again indium gallium oxide, actually with that high gallium concentration, 40% as I just showed, but it is hydrogen doped. And what has been observed is that hydrogenation, actually that's a solution processed amorphous oxides, they showed 70-fold mobility increase, especially with gallium. So experimentally, they tried zinc and different gallium concentrations. So actually the effect is the best. The more gallium we have, the better the mobility increase, the higher the mobility increase. So what we found here from the theoretical calculations is again, long-range structural changes upon relaxation after hydrogen being introduced into indium gallium oxide occur in this system. And here what I show is the change in the effective coordination number or the distortions of the metal atoms. So purple represent indium, green gallium atoms. And they are shown as a function of the distance from the hydrogen. So we can see that we have significant changes, for example, in the distortions of gallium, even far away, up to 10 angstrom away from where the hydrogen is located. So this is the clue that we have very extended bond reconfiguration and rearrangement is the network as we introduce a dopant or create a defect, in this case is hydrogen, and we have this energy gains due to this relaxation and reconfiguration that actually outweigh the passivation. So hydrogen here, unlike silicon oxide, well, it does passivate the dangling p orbitals, those defects say that I showed earlier at the balance, top of the valence band. But energetically, actually, it's not the main origin for the defect formation, and bond reconfiguration and rearrangement actually outweigh energetically this passivation of dangling bonds. So the hydrogen introduces these changes in coordination, distortions, and morphology that actually favor more uniform charge density in the conduction band. And hence we have an enhancement in the mobility overall for the material. Well, I was talking about the mobility as just this connection to the morphology, but of course it's a much more complex phenomena. And I would say that actually mobility is much more complex than the crystalline materials, because there are many factors that are in play that we have to consider for the scattering in these amorphous oxides. We have to look at the defects and actually determine what kind of defects we have. We have to look at the composition, strain, phonons, and crystallinity, nanocrystalline inclusions. So all the different levels, from the local interactions to sharing spatial distributions of the chains or clusters, and then nanocrystallites, they all affect the mobility, overall mobility of the system. So it's much more complex, and of course computationally it's still a big challenge how to combine all these factors in order to be able to predict the mobility. Well, so far we talked about the deposition temperature and metal composition. So let me go now into the oxygen stoichiometry and look at non-stoichiometric cases and defect formation. So here, first I'm comparing the crystalline and amorphous stoichiometric indium oxide and looking at the local structure of individual indium and oxygen atoms. So of course we also have a distribution in the coordination number. So here is a coordination as a function of distortion of the polyhedra, or coordination, the same coordination as a function of distances in the first shell only for the indium or for the oxygen. And oxygen actually probably is more significant because it's a p orbital, so it's more directional bond. So there are more actually preferences for the angle and coordination in general than for the indium oxide that is an s orbital. But the point I would like to make here is that comparing to the crystalline material, which are only just a few dots, because most of the atoms, of course, have exactly identical coordination and distances and distortion. So if we compare crystalline to amorphous, we can see that there are only 4 indium atoms out of 540 within the realizations that we've done for amorphous indium oxide that have the structural values, meaning coordination, distances, and distortion combined, that match those in crystalline. So amorphous is very, very far away from what we have in the crystalline material, and distribution is actually plays a significant role. So on average, of course, we can find some dependencies, but I will argue that these outliers that we are seeing, the tail states in the distributions, they're actually playing a significant role in the reconfiguration, right, in the bond reconfiguration, and in general in the defect formation. So this was stoichiometric. We have exactly the same, the perfect stoichiometry of the material. As we change to non-stoichiometric, so reduce the oxygen content, of course, we begin seeing much more outliers, much lower configuration here. For example, the coordination becomes 3, or maybe even 2 for some cases. And so we'll start developing localized states as we go to more and more non-stoichiometric cases. But again, we would like to compare to the oxygen vacancy that has been studied a lot in these oxides, and try to develop essentially the descriptors for the structure. What should we look at exactly in order to being able to predict the formation energy of these defects? and the electronic properties. So we are looking not only at the coordination, distances, distortions, but also looking at the nearest neighbors and sharing between the different nearest neighbors. So here we can see that if the vacancy in the crystalline indium oxide creates the nearest neighbors that are becoming 5 coordinated, down from 6 in a perfectly stoichiometric indium oxide, we have a huge number, actually a huge fraction, about 30% of all the atoms in amorphous that have similar, structurally similar, at least in the matter of the local structure, the coordination and the distortion, to that vacancy surrounding. So what we find is that the vacancy in crystalline indium oxide looks like this. So we have a strong localization of this. It's a deep defect, in fact, in indium oxide. And we have strong localization of the electrons right there on the vacancy side. So we can schematically show that the vacancy looks like that in the crystalline material. Yet as we go to amorphous, this big network of undercoordinated indium oxide, indium atoms, the 30%, as I mentioned to you, they share the lack of oxygen with each other. So because of that bond reconfiguration and weak bonding and rearrangement, the vacancy looks like that. It's an extended state, and actually we have a shallow and delocalized conduction band, even when the oxygen stoichiometry is as low as to 0.93, so below 3. It's a large defect concentration, oxygen defect concentration, but still we end up with extended shallow state in this, we call it high quality amorphous samples with delocalized conduction band. Of course, as we start reducing the oxygen concentration, we start to have even lower coordination of indium, and localized states appear. So now we do see some similar patterns in terms of the structure, coordination, and distances to the oxygen vacancy. But the point is that these various degrees of electron localization associated with this isolated, severely undercoordinated atoms, they may follow by clustering of these metallic indium-indium bonds, or even complex metallic networks when we go to very highly non-stoichiometric oxide. So again, the long-range structure really determines the localization and the electronic properties of these defects. And we need to look at the medium and long-range structure to describe the properties. So here, this is the, again, the electronic properties of the indium oxide as a function of oxygen content. So I showed you the very delocalized conduction band before for even slightly under-stoichiometric material. So this we call high quality annealed samples. We have only shallow states, delocalized. So the structure allows to have these defects and be conducting with good conductivity, low scattering. But when we decrease the oxygen stoichiometry further, or maybe in S-grown samples, we may have a strong electron localization that negatively affects the number of carriers, the charge transport, and as well as optical transparency and device stability. So all these defects appear below the Fermi level and affect the properties significantly. To deal with these states, these localized states, there are many ways. Of course, we can again try to anneal the sample, or we can do it with the metal composition. So here it's a very complex slide because the role of metal composition is very complex. I already mentioned about the mobility, but of course it affects a lot of parameters, crystallization, mechanical properties, optical band gap and work function and so on. So here I just highlight that the carrier concentration indirectly, again, we cannot really dope the material to introduce extra carriers because usually the dopant assumes the coordination that it wants, but indirectly we can help control the number of tail and traps electron states and help with the device stability. So here an example of boron doping where indeed we showed both experimentally and theoretically that we were able to put these deep traps states much deeper in the band gap, and that helped with the device stability tremendously, actually. So there are ways to control it, but again, of course, we need to consider a complex effect of the metal composition on the properties in general. So finally, I would like to mention the geometrical constraints. So this is just very recent result that we have started looking at. Again, these materials are important for many devices. And so surface states and interfaces, functional interfaces are key here. And I mentioned that we know already experimentally that typically we have very smooth surfaces, but still the origin and the structural properties at the interfaces and surfaces are not that well understood. So here, this is indium gallium zinc oxide, one of the most actually utilized material in the flat panel displays, for example. So technologically, the IGZO is mostly commercially used. And here I'm showing just quickly the structure, crystalline structure. It's a layered structure, amorphous bulk, and then amorphous slab. So we introduce the vacuum region and quench several slabs, liquid quench several slab structure. And after the relaxation at room temperature and then relaxation at zero temperature, what we find is that the surface energy is very, very low for this material, as well expected, again, because of the long reconfiguration. We have the very featureless, structurally featureless surface in these oxides. So again, due to the significant structural relaxation throughout the entire slab, that results in a very smooth surface. Of course, the coordination is affected quite significantly. So here on the side, you can see the coordination of indium, gallium, or zinc, and especially in indium and zinc, the coordination is significantly lower when we come close to the surface. So around within 2.5 angstrom, the coordination drops significantly down. Here, the shaded region is the coordination ranges in bulk. So no surface effects, just the amorphous bulk, and the average for the bulk and for the slab. So for all atoms, not only indium and zinc, that show significantly lower coordination, but also for gallium, the average is significantly actually low throughout the entire slab. So the geometry really affects this coordination significantly, yet the states in the conduction band remain delocalized. So that was a very interesting fact that we found that still the conduction band is delocalized. We don't see the strong localization unless we go to highly non-stoichiometric material. For these oxides. Tail states in the valence band, of course, increasing.
Just letting you know that you're running out of time.
Okay, sure, yeah, I'm actually, so let me go to the final conclusions. So I hope that I was able to show that defects in amorphous oxides differ fundamentally from those in covalent materials and also from point defects in the crystalline oxides. And we must consider these defects along with the evolution in the disordered structure. So to understand the properties, we cannot do it separately. We have to combine and look at the medium and long range ordering as well. And just to connect to Aaron Walsh actually question that, I think that we have investigated quite a lot of materials, and right now one of our goals is to put a database. So these are a listed material that we already looked at, and so the idea is to have this genomic standardized database with data and tools to look at these materials in order to hopefully use some machine learning, AI, to be able to predict the properties of these oxides. Thank you.
All right, thank you very much, Julia. That was really interesting, and yeah, there is a question from Himanshu Jain on the chat. He asks, how does substrate roughness affect the film's surface?
That's a very good question, and well, we didn't look at well, many specific cases. So here you can see that there are several cases. We look at the silicon, actually crystalline silicon covered with the oxide, and molybdenum oxide with indium oxide interfaces. So of course, from the point of view of modeling, it's very hard to model the roughness, right? We really need huge supercells in order to do that. But at the same time, from the smaller cell that we've seen, we see that we do have the we do have the oxidations, of course, we are seeing it, and we're also seeing the coverage, and having the amorphous material really helps because of that. Again, reconstruction and readjustment in the structure, it helps significantly to grow an amorphous layer on top of a rough crystalline layer.
Okay, thank you. Are there any other questions? If not, then maybe I can ask one. I was just wondering what the, so you've discovered these chain-like structures, which are sort of the microscopic enabler of conductivity. I was just wondering how much, if those have been identified sort of in, I don't know, diffraction, or if there's any direct evidence of these chains.
Thank you for that's a great question. Yes, of course it's hard to see right on such a level. What we looked at is actually the optical response and optical properties. And we do see in the IR spectrum, we do see the enhancement in the absorption near the peak. So we identify that indeed, because of that lower scattering when we have the chains, we are seeing it optically. So otherwise structure, of course, it's very hard to resolve it and identify. And if I'm showing the chains, of course, in a small structure, in a real sample, they are all interconnected, right? There is no direction to this chain. So that's why it's well, essentially impossible to identify these on the traditional methods. But also I think the issue is that we have such a dynamics in these structures. Actually, I wanted to mention that, well, since you also let me go to this slide, that the relaxation of this conductivity is very, very long. So the measurements showed, for example, for indium gallium zinc oxide, it took about 6 months actually to measure the photoresponse. So the dynamics in this structure is really significant. And that's why the static characterization is not really appropriate for this system. So whatever we are measuring statically, if we want to get these chains, it's not enough, right? We really need to look at the transient response and the dynamics in this structure. So that's why it's very challenging to find those chains.
All right, thank you very much, Julia.